Up here, and hopefully this will come across in presentation mode. Uh, yes, thank you so much, Suresh. It's great to see you again, and Tushar and the rest of the organizers. What a amazing event, and certainly a unique event. And it's a privilege for me to be here with you guys and help kick it off with this keynote here. So the keynote I'm going to give is what I call the RF engine of the 21st century. And Suresh gave a bit of a background to me. I'll give a little bit more. As you mentioned, I'm CEO of Mini Circuits as of 2023. I've been in industry for about 30 years now, mostly in the RF microwave millimeter, but really essentially all the way from the DC range up to the optical range, and a full set of experience across test and measurement, telecom, satcom, and RF components and systems. And as Suresh mentioned, all the way back to HP. So I feel very honored to have worked at all of the different companies through my career. Very fortunate, and I've had the opportunity to work with some amazing people and around some incredible technology. So I'm happy to talk with you guys today about what I call the RF engine of the 21st century. And as I think about this, as we prepared these slides for this conference, I wanted to go back in history a little bit and talk about, where does it all come from? Because everything we do is really based on how many amazing things have been done ahead of us. And I was reminded of this when I was back studying at Stanford under Professor Tom Lee. And I remember he would always start with a bit of history. And so I'm going to use a page from his playbook and start with history. Then I'll talk about some of the enabling RF technologies and the application associated with that. We'll get to where we are as a state of the art, and then we'll talk a little bit about the road ahead. So to the foundational theory, now all of the engineers will enjoy seeing some equations on the slide, and some of these will be familiar to you. And this is a sampling of some of the folks, some of the people in history that have really made it possible for us to do what we do today. Go back to primarily to the 19th century, and you had Michael Faraday. Faraday's law of induction. Faraday was an experimenter, but his experiments really helped shape a lot of the theory that was happening all around him. And without his sort of knack for experimenting and uncovering things, we wouldn't have things like inductors and transformers. He helped guide that. It was him who led that in the early days by detecting electric currents and magnetic fields. And then if you're in the microwave world, which of course many of you are here as part of the MTTS Society, you'll know Maxwell, and maybe you'll have some painful memories of Maxwell. And if I was to ask you how many equations Maxwell actually came up with, many of you would probably say 4. And it turns out that the original equation that Maxwell came up with were on the order of 20 equations. And those actually turned into the 4 that we all recognize today, and maybe we partially understand. The 4 came from Oliver Heaviside. He actually took the original 20 and part trying to understand exactly what Maxwell had theorized, they simplified, and these are the 4 equations that actually showed up, and these are the ones that we study and we learn with the dot products and the curl products and the partial derivatives. It didn't mean a whole lot, it seems, back when Maxwell was coming up with it, and nobody really knew how impactful that would be. But it formed essentially a theory of electromagnetism, which is what everything we do today is based on that theory. I've yet to go out to the old Maxwell house, and I've got to get out there and visit and take a look at some of those historical places where he actually came up with some of these theories. Someday, that's on the list of things to do. But we owe a large debt of gratitude to Maxwell. And then in parallel, but after succeeding Maxwell was Hertz. And I call out Hertz. There were several others again in this era. But Hertz actually, his job, it was to understand Maxwell and actually prove, did Maxwell theories actually, were they true? Did they really, were they true in real life? Could you prove them? Could you measure them? And there was a guy named Helmholtz, who some of you will remember also for things like the wave equation. And he actually as a professor, guided Heinrich Hertz to prove Maxwell theories. And Hertz did that. In the meantime, he developed or produced and then detected what they called at the time Hertzian waves, which now we call radio waves. And it proved that there was indeed waves, and they operated and functioned the same way that Maxwell had theorized, and that radio waves and light waves are actually part of the same family. And so when we look at the frequency spectrum today and we think about, hey, what bands are we going to use for any particular application? That all started with the electromagnetic spectrum. And that all was formed back in the 19th century. You'll see none of these folks lived into or past 1900. So these were the giants back in the 19th century. They formed the foundational theory that so much of our work is based on. Right behind them came some of the pioneers. These folks actually took that theory and those experiments that had proved electromagnetism and some of the fundamental workings of the components. And they put those components and building blocks together. And it was Marconi who's recognized as the father of telegraphy. He conducted experiments and showed that you could propagate signals and you could communicate over long distances. It was essentially the basis of what we do today in terms of RF and microwave transmission and receiving. In a little bit of a different path was Tesla. Today, Tesla is known as a car brand. And back in these days, Nikola Tesla was battling to prove out alternating current, AC. He had a fight about which was more important, AC or DC. But the way that he developed his ideas, they opened up so many more avenues and so many more paths. And again, transformer circuit sort of came out of what his inventions were, the Tesla coil. And these now find themselves in many, many applications. And then somebody a little bit more recent again was Armstrong. And many of you will remember the Armstrong receiver. And this one I actually do go right back to when I was in class learning about this. And Armstrong was a common one that we would talk about. But this formed the basis for many of the things I did in my career too, the super heterodyne receiver. And that was developed by Armstrong originally. It helped form the theory of frequency modulation, which ultimately turned into FM radios, of course. And that was all fundamental blocks for modern radios, which is essentially how we communicate today, one form or other of a radio. So I wanted to acknowledge, we're very fortunate. These are the folks, and this is just a small sampling of some of the folks, some of the people, some of the amazing thought that went into the theory and the practice and the initial ideas. And then if we go forward, so what are all these RF technologies that have emerged out of these great thought leaders, these great experimenters, these great theorists? And all the way back, this timeline shows all the way back to beginning just before 1900, all the way out to 2000. And, we had the Tesla coil. Early 1900s, we had the vacuum tube was invented by De Forest, called the Audion tube at the time. You kind of go forward, you'll see the Armstrong mixer, the heterodyne architecture. The theories of Nyquist were forming in the early 1900s. Ultimately, it got called the Nyquist-Shannon or the Whittaker-Nyquist-Shannon theory about sampling. All of that was in the 1900s, and then Shannon came along actually much later. His name got attached to that theory, but he actually came a lot later, and he formed this Shannon-Hartley theorem around channel capacity in the 1940s. And kind of go along and see all the different technologies that were being developed, the magnetron, the PCB, and again, I'll bring back some fond memories for everybody with the Smith chart. Many of us have spent time working on this Smith chart, drawing patterns, interesting patterns on this Smith chart. It was invented back in 1939. And it wasn't that long ago. I think that's one of the things I want to draw to your attention as I talk through this is these things actually were not that long ago. You know, if you just go back, this was just 80-ish kind of years ago that the Smith chart was formed. And you think about all of the different things we've accomplished using the Smith chart. The printed circuit board was right there, the magnetron, the first transistor back in 1947. And then moving forward again, I'll get into some of these areas, you know, as we talk through the different types of integrated circuits. The first practical integrated circuits in the 1950s. Compound semiconductors were discovered somewhere in the same sort of era, a little bit after perhaps, or right around the same time frame. And I want to give a lot of credit to the folks who we stand on their shoulders, the theoreticians, but also all of the practicing engineers who use a Smith chart and develop products like the first spectrum analyzer. We owe a lot, and we may not recognize it all the time, but when you're in the lab, you really can't get a whole lot done without the spectrum analyzer. And in fact, the world's first network analyzer came out soon after that. And a lot of what we do today has to be tested and measured. And so I spent a lot of time in the test and measurement industry, and I recognize how important those products were to prove the theory and make the measurements that really showed the types of products and the types of technologies and show that they work the way that they were supposed to work. You go forward into the 70s, the first mimics were developed in the 70s. There was a lot of new design tools coming into play, EDA, simulation software, and that really helped advance the types of technologies you could develop, the types of components you could develop, and then ultimately the types of systems you could develop. So we got more and more complex, but also more and more easy to develop these technologies. And what happens is you'll forget Maxwell at some point, and you'll be using EDA software. And it turns out all of that is based on Maxwell theories and many of the other people that founded the theory of electromagnetism and RF communications. And then you go forward to PHEMT, et cetera. You go to 3D modeling and IPDs, integrated passive devices, et cetera. There's so many amazing things, and this chart is just a reflection of some of them. But what happened is, with the great theory that had been formed in the century prior, we were able to develop a lot more tools and then develop a lot more enabling technologies. And that's what you see here in this chart. And I'm going to go forward one slide here to the applications that were enabled. Again, a bit of an eye chart here. You'll see the progression all the way back to, again, the late 1800s, when Heinrich Hertz demonstrated radio waves and Marconi patented the radio before 1900. But then there was a proliferation of new technologies that started coming out and applications powered by those technologies. So all of this falls behind the development of the technologies and behind the tools that were created as part of this. And one of the interesting ones is radar in 1939. So the war, as ugly as it was for the world, actually advanced a lot of the technologies that we use today. That period from 1940, late 1930s into the mid 1940s, a lot of interesting technologies were developed. Radar was one of them. Pulse modulation, jamming, direction finding, a lot of the things that are used today in military, aerospace, defense applications, but also in regular commercial communications came out of this era. Somewhere along the way in the 50s was something called a maser, which somebody thinks, which you might think is a misspelling of the laser. And it's actually almost exactly the same thing, except it's based on microwaves instead of light. And going forward, you'll see things like satellite communication systems coming together. I like to think of Arthur C. Clarke, who was writing story science fiction back in this period. And he came up with the first satellite concept, actually, with geostationary satellites. And it was just a concept, just a theory. And it didn't take long before that turned into something practical, thanks to all of those incredible components that have been built, but then also the great test and measurement products and the great tools to build more complex systems, including, of course, a lot of computing power behind that. And it just sort of boomed from there. You had microwave ovens and applications like that. Spread spectrum communication came into play. One of my favorite stories is certainly around how the cellular phone developed. And a friend of mine, Marty Cooper, was original, what I would call the father of the cell phone. And I've had the privilege of meeting him, spending some time with him in the past. And, you know, he created, you may not like me calling it the brick phone, but I think that's what a lot of people called it back in the early 80s. And it was a large phone, but it was the first cell phone. And then that really set the path for 2G, 3G, 4G, and now here we are all the way at 5G, heading beyond 5G. In the meantime, a lot of wireline technologies like DOCSIS for cable TV were all emerging and expanding. And the world of satellite expanded even further into multi-orbit constellations. And now we have massive LEO constellations, and I was fortunate to work on one of those until I became CEO of Mini Circuits at Project Kuiper with Amazon. An incredible effort, very similar in some ways to some of the other ones happening with what was started by OneWeb and then Starlink. And Kuiper is another one of these with this massive LEO constellation. And that will open a whole lot of other applications. Behind this, we have autonomous vehicles, which many of you are driving versions of vehicles that have various levels of autonomy. And if Elon Musk is right, soon we'll have full self-driving. I wouldn't count on next year, but maybe soon. So RF is everywhere at this point, right? This is kind of the current state of the world. This image kind of shows it in a way. It signals propagating all over the place. And look at that image for a second, and you'll think that's a pretty strange image. And I'll come back to that image later in my talk here. But the idea is that RF is propagating all over the place. Communications, mobile wireless communications, wired communications, commercial satellite signals coming from space, signals going deeper into space for that matter to go do some further research into the universe, many military and defense applications. And we all hope that the emphasis is very much on trying to set up good defense systems. And that includes comms, includes a lot of radar applications. And then there's a lot of emerging commercial applications. Automotive, I mentioned a little bit. It's a whole nother world in terms of how cars operate today versus how they operated 40 years ago, even 20 years ago. And RF energy is an area, new space with the LEO satellites and the constellations. And quantum computing is another one. And I'll move on to what I call the road ahead, with where are we going with a lot of these new applications. And the point of my talk this morning, of course, is that this is very much all based on RF technology, and without the history, without what I talked about and those original thought leaders, the experimenter theorists, we wouldn't actually be at the point that we are. And now the world seems like it's just beginning, actually. In many ways, it feels like we're just at the start of this journey, which is remarkable because we've come a long way in a very short amount of time, but we've got still a long way to go. And we've got some really exciting things happening. I'll start with 5G and where does 5G go? And we had FR1 and FR2. FR1 was the technology primarily below 6 gigahertz, frequency range 1, and then frequency range 2 was millimeter wave. And I think there was a lot of excitement about 10 years ago, 10, 15 years ago, maybe even 5 years ago on the millimeter wave part of the spectrum and of 5G. And it turns out that it didn't really latch on as much as we would have liked, perhaps. And different things can sort of play into that. And there's a lot of debate that could occur as to why or why not. In any case, 5G did move millimeter wave forward a fair bit. And now we look at where does it go from here. And it's interesting. One of the areas that is being researched is what's called FR3. And instead of FR3 being higher frequency than FR2, it's actually in between FR1 and FR2. And I have an image here of some of the folks at NYU Poly. A good friend of mine, Ted Rappaport, is in the middle on the left. And this is his lab. And we have some of his PhD students here. And then we have some folks from mini circuits on the right of the image. And what this was, and we got the block diagram for you in case you want to look at it. This was a block diagram put together mostly with mini circuits components. And it actually was a channel sounding system. And what its purpose is to model the frequency ranges 5 to 17 gigahertz. That's now coming into the World Radio Conference as an area that is being explored more. And it's very possible that FR3 becomes part of either future versions of 5G or 6G. And at the same time, 6G is exploring sub-terahertz bands. So there's another really good area being explored. Behind that are supporting technologies. A lot of these components that are being built by companies like ours and many others out there. And they're pushing deeper into millimeter wave and also filling out the other bands in microwave. Including bringing in waveguide components more and more for test and measurement applications. So I'll move along to automotive. There's a lot of connectivity in the cars, outside the cars, with the infrastructure around it. All of this is wireless technology. There's a lot of really good things happening, like child presence detection using 60 gigahertz. This is where sensor fusion is occurring. As you can kind of see on the image, there's a lot of sensors that are coming to play here. And again, the supporting technologies need commercially viable components. SWaP-C, which is size, weight, and power. And I'd like to put the C in there, and some do and some don't. But in this market and application, C, which is cost, becomes really important also. RF energy is another expanding, booming area, emerging, beginning to boom. It's a shift away from some of the magnetrons and more towards solid state technology. Once you bring solid state technology into these areas, there's a lot of possibilities. And these possibilities could be in applications in any sort of industrial application. And I've seen many that require RF energy. Semiconductor requires kilowatts of power, and many medical applications. And so a whole array of applications here. LDMOS was sort of the core behind this, and that's moving gradually towards gallium nitride, and a lot of passive devices behind that, but a lot of interesting software and a lot of smart technologies. I couldn't present this keynote without talking a little bit about commercial satellites. I came off of that about a year ago as I joined up with mini circuits, and this is a fantastic area, very interesting in terms of the technologies coming in and what it opens up in terms of possibility for communications and for sensing, a lot of applications. And the bands are getting filled up all the way from the lower K bands, all the way up into the E band even for communications. And the work here is commercial, it's also industrial, it's also government. And government, likes optical links. A lot of us do from the standpoint of high gigabits of data rate, but also because it's very secure. Again, supporting technologies, the fundamental technologies are going to be very similar, and they just need to get better and better as we go. SWaP, again, is an important factor here. Quantum computing, another incredible growth area. I see MTTS has this as one of its focus areas. I think Maurizio showed this as the second one around quantum technologies. And again, it'll use a lot of RF microwave components, and it'll actually require some reasonable power amplifiers. And then the last one I'm going to go to, I know I'm coming right up against time here. I could not have this talk without showing AI, of course. And AI is, as Maurizio said, one of the key focus areas for MTTS going forward here into this year. It's a mega trend, of course. You guys all know that. And this is a little bit of a flip in this case than the other ones, where in the other ones, You know, I talk about the market trend and the supporting technologies. In this case, AI is likely going to be one of the supporting technologies to advance what we can do in the world of RF and microwave. So it sort of flips around a little bit, and it could, again, I'll use the word could because all this stuff is being tested and teased out. It could shorten design cycle. It could end up providing faster ways to come up with new circuit technologies and topologies. And ultimately, what it can do, it can free engineers to focus on other areas. And if you think about it, how often do you now go back to the Smith chart? Hardly ever, because the EDA tools enable you to not have to go there, and because the test products enable you to not have to actually think in terms of the original theories that you learned perhaps in school and in college. It gets more and more abstract as you go, and you'll see this image on the right, which is an AI generated image. And the image is a very interesting image. If you look at that and you say that's some kind of form of art, it's probably more art than science. It was intended to show communications and test and measurement and EDA tools. And it was fed this request to put together an image, bringing all those things together. And this is what it came up with. It probably doesn't make a whole lot of sense to anybody at this point, and that's okay. That it wasn't going to make a lot of sense yet. But this is what AI is. I think it's still in the child infant stages. The image I showed earlier where I described a lot of wireless technology all around cities and stuff, once you see the slides later, you'll see that things are out of proportion. Things don't actually line up all that well. There's base stations taller than skyscrapers, for instance. In any case, AI is going to evolve, but I think we're in the very, very early stages of it. And I think it's great that we're going to get to superpower or supercharge our future developments with AI. And that really is my last slide. I'm going to end with a quote from Arthur C. Clarke. Again, he came up with many, many great ideas. 2001, A Space Odyssey, but the concept of satellites. And what happens is the further we go, the deeper we go, the more we forget sort of what's behind the scenes. And us as engineers and technologists, we end up probably being the last of the group that will continue to understand what's underneath the curtain. But to everyone else, it'll look like magic.